17.7 beats. Interference in time. In this session, we will explore the fascinating world of beats and temporal interference. We will begin by looking at a practical example involving resonance in air columns to measure frequency. From there, we will define the physics of beating and move into the mathematical representation of how these waves interact. Finally, we will discuss the concept of beat frequency, its real-world applications in tuning instruments, and the important distinction between the physical measurement of frequency and our psychological perception of pitch. To understand resonance, let us look at an experimental setup. We have a vertical pipe that is open at the top and partially submerged in a container of water. The surface of the water inside the tube acts as a closed end, reflecting sound waves back upward. When a vibrating tuning fork is held over the opening, standing waves are created if the length of the air column matches a resonance frequency. The first resonance, or the fundamental frequency, occurs when the length of the air column is equal to 1/4 of the wavelength. As we move the pipe and change the length, we can find the second resonance at 3/4 of the wavelength and a third resonance at 5/4 of the wavelength. Let us analyze a specific case where the smallest length for resonance is 9 centimeters, or 0.0900 meters. To find the frequency of the tuning fork, we use the speed of sound, 343 meters per second, divided by the quantity 4 times the length. This calculation gives us a frequency of 953 Hz. We can then determine that the wavelength is 0.360 meters. Based on this, the next two resonance conditions occur at longer lengths. The second resonance is found at 0.270 meters, and the third resonance occurs when the pipe is raised to 0.450 meters. It is important to distinguish between two types of interference. Spatial interference occurs when waves of the same frequency overlap, creating a pattern where the amplitude varies based on position in space, such as the standing waves we see in a pipe. Temporal interference, however, involves the superposition of two waves with slightly different frequencies. Instead of a pattern fixed in space, this creates an alternation between constructive and destructive interference over time at a single fixed point. This time-dependent phenomenon is what we call beating. Beating is formally defined as the periodic variation in amplitude at a specific point caused by the overlap of two waves with slightly different frequencies. This variation creates a pulsing sound rather than a steady tone. The human ear is quite sensitive to this and can detect these individual beats up to a rate of about 20 beats per second. If the difference in frequency becomes larger than that, the individual pulses happen too quickly for our brain to distinguish them, and the beats blend into a single, complex sound. Mathematically, we can represent this by looking at two waves with equal amplitude but different frequencies, labeled frequency 1 and frequency 2. When we combine these, using the principle of superposition and trigonometric identities, the resulting wave function has two distinct parts. The first part represents a wave vibrating at the average of the two original frequencies. The second part is a slower-moving envelope wave that modulates the amplitude. This modulation occurs at a frequency equal to half the difference between the two original frequencies. This describes how the loud and soft pulses of the beat are structured. The visual representation of this resultant waveform helps clarify the concept. In the top graph, you can see the two individual waves of different frequencies shown in blue and green. When they are added together, they produce the red wave shown in the bottom graph. Notice the dashed line tracing the outer edges of the red wave. This is the envelope wave. The amplitude of the sound reaches a maximum twice during every single period of this envelope wave. This illustrates why the pulsing sound we hear is directly tied to the way the two original waves move in and out of phase. The beat frequency is the number of amplitude maxima, or loud pulses, heard every second. Because a maximum occurs twice during each cycle of the envelope wave, the beat frequency is simply the absolute value of the difference between the two original frequencies. For example, if you have two tuning forks, one at 438 Hz and another at 442 Hz, they will produce a combined tone with an average frequency of 440 Hz. However, you will also hear a distinct 4 Hz beat, meaning the sound gets louder and softer 4 times every second. Let us apply this to misattuned piano strings. If we have two identical strings originally tuned to 440 Hz, and we increase the tension in 1 by 1%, its frequency will change. Since frequency is proportional to the square root of tension, the ratio of the new frequency to the old frequency is the square root of 1.010, which is 1.005. This makes the new frequency 442 Hz. When both strings are struck together, the resulting beat frequency is the difference between 442 and 440, which is 2 Hz. A common pitfall in physics is confusing pitch with frequency. Frequency is an objective, physical measurement of the number of oscillations per second. Pitch, on the other hand, is a subjective psychological reaction that allows a person to perceive a sound as being high or low on a musical scale. While they are closely related, frequency is the physical stimulus and pitch is the human response. Because pitch is a perception and not a physical property of the wave itself, saying the pitch of the sound is a certain number of hertz is technically incorrect. In summary, beats are the result of temporal interference between two sound waves that have slightly different frequencies. This interaction causes the sound intensity to fluctuate at the beat frequency, which is equal to the absolute difference between the frequencies of the two sources. The shape of the combined wave is defined by an envelope that determines the rhythm of the pulses. This is a practical tool for musicians who listen for the beat frequency to disappear as they adjust the tension of a string to match a reference tone. To wrap up, consider these review questions. First, if two tuning forks produce a beat frequency of 5 Hz and one is known to be 256 Hz, what are the two possible frequencies for the other fork? Second, think about the process of tuning a piano. Why does a tuner listen for the beat frequency to decrease rather than increase when tightening a string to match a reference tone? Reflecting on these will help solidify your understanding of how frequency differences translate into the sounds we hear.